Hello. In this video, we are going to look at portfolio models. That is, at models that are going to measure the credit risk of a portfolio of loans or bonds. This is obviously very important for banks that typically have large portfolios of loans, and the stability of the bank depends on the performance of that portfolio. So our goal in the end is to come up with a value at risk type of measure. But since this is applied to a portfolio of loans or bonds, we will call this a credit value at risk. There are two important notes here. One is that correlations are very important. We cannot ignore the fact that defaults are correlated. In recessions, there are many defaults. So it's critical to input correlations. However, it's hard to estimate correlations based on empirical data because there is not much data on defaults. So this is one more case where the Mertens model is going to be very useful, and there is a very nice solution developed in the industry by JP Morgan, which does exactly that, uses Mertens model to overcome this lack of data issue. So that's the model we're going to look at in this video. A second note is that there is a difference relative to the usual stock market returns. You can look at this figure here. The typical market returns are like this, more or less normal, but credit returns are very different from normal. So credit returns have this shape here, which is clearly skewed due to the fact that we have in some cases we have heavy losses and the upside is limited. So whereas in the standard value at risk analysis we can sometimes use a normal assumption and just use the mean and the variance to estimate a critical loss, in this market, in credit markets, we cannot say that this is a normal distribution. So we cannot use a mean and variance and estimate the critical value using just those two moments. We will actually have to estimate the full distribution and compute a critical value, a value at risk threshold using the full distribution. Okay, so the model we're going to look at is this model developed by JP Morgan called Credit Metrics, and more broadly this is known as credit migration approach, because this is basically the underlying driver here is that the firms are going to migrate through credit ratings. All right, the assumptions of the model are as follows. The only source of uncertainty is credit migration. So we're going to get a ratings matrix, and firms are going to migrate over that transition matrix. Given the rating class, then all firms are the same. So if a firm has a single A rating, then it's the same as another firm with the same single A rating. The third assumption is a simplifying assumption, just because we cannot handle everything at the same time. We are just going to assume that interest rates are deterministic, so there is no uncertainty. What will this help us with is that we are going to compute bond values in future dates, just using the forward rates that we can observe in the markets today. The fourth assumption is that equity value is a good proxy for the value of the assets of the firm. So recall that in Mertens' model, the driver was the assets value, but that is not observable. So what we're going to do is use equity as a proxy for the unobservable asset value. So in particular, we're going to use equity values to estimate correlations. There are two building blocks in this model. The first one, which is just for one single obligor, and then the second building block, which is the real thing for the whole portfolio. So in this video, we're going to look at the first block, and then in the follow-up video, we'll look at the second block. Okay. These examples we're going to look at here come directly from this document published by JP Morgan. This is available online. It's an excellent document, not only for this specific issue of credit risk, but in general, there's a lot of finance concepts that are very well explained there. So definitely something to read. Right, so let's start with the first building block, the single exposure risk. So let's say that we want to estimate the change in value that one single bond can have over a given horizon. Let's say it's 1 year, okay? And for example, let's suppose that the bond we are trying to value is this 5-year, 6% bond that now, today, has a BBB rating, okay? So what we want to do in the end is to find out what is the possible price of this bond 1 year from now. So the first step is to get the transition matrix. This is a similar matrix to what we have seen before. Let's look at the matrix. What we are interested in is this line here, this row here, because our bond is BBB. So we basically were interested in these numbers, which is the probability that the firm will jump from BBB to AAA in 1 year, 0.02%, jump from BBB to AA, and so on, remain BBB, 86-93%, and so on, default with a probability of 0.18%. The second step is to estimate the recovery rate for this bond. Okay, we discussed the recovery rate in previous chapters. Let's just say that we estimate for this bond the recovery rate to be 51.13%. So this is relevant for the case that the bond jumps from BBB to default. So this event here with probability 0.18%. And what we are saying is that if that happens, the bond will be worth just 51.13%. Third step, we need forward interest rates. Let's say that we have estimated interest rates for different rating categories, and we come up with these numbers for different horizons. So this is the forward rates for AAA, the forward rates for AA, and so on. So now what we need to do is we have to estimate the value of our bond at the end of the year for all possible cases, right? So for example, if the bond that is now BBB upgrades to single A at the end of the year, the value that the bond will have at the end of the year is given by this, right? So let me just open a figure here just to make this clear. So the case that we are looking at is we have this bond that starts at BBB today, and it's going to jump to A after 1 year. We are here at time 0. At time 0, the bond has all these cash flows, the coupons plus the face value, and we want to find out what will be the value of the bond here at time 1 if, again, it becomes A at that moment, right? So what we're going to say is that the value of the bond at time 1, if it goes to A, is the value of the cash flows using the discount rates that are for that rating that the firm is now, which is A, right? So the value will be 6%, this coupon, plus this coupon discounted at 3.72%. What was this 3.72%? Was the forward rate computed here at time 0 for the period between 1 and 2 for the A rating category. Plus this 6% discounted at 4.32 for 2 years, and so on until the end. The last cash flow discounted at the forward rate for the A category, which was 5.32% in the table in the previous notes. So the value that the bond will have in that case is this one here, 108.64. So that is the value that we have here. This is not exactly the same thing because these tables again come directly from the JP Morgan document, and there's probably some small rounding. So I have 64, they have 66, but in any case it's this case here. And I can do similar type of calculations and get all these other values. So the only thing that changes from, say, this row to this row is that instead of using the A rates, like this row here, I would use the BBB rates and get 107.55 and so on, get all the other values. Okay. So having that, we can now compute the credit risk measures that we want. So this table here repeats the information we had before. This is the probability of each state. Again, this comes from the transition matrix from the row for the initial state, triple B. So it's this row here transposed to become this column here. This is the values that we just computed. So for example, the 108.66 is this number here. The other numbers come from this column here. And basically that's it. So now I can just multiply these two columns and get the sum of all those multiplications becomes the mean, the expected value of the value of the bond. And then this column here is the difference between the value in that state and the mean. So basically this tells me whether I have a gain or a loss relative to the expected value. Okay? And now what I care about is this loss. For a value at risk type of measure, I'm going to look at a very high loss that is only exceeded in a small number of scenarios. So let's say I want a 99% value at risk, meaning I want a loss that is only exceeded in 1% of the cases. So to get this value, I would start adding up the probabilities until I get to 1%. So 0.18% is not enough yet, so this is too much. 0.18 plus 0.12, that's 0.30%. So this is still too much. 0.3 plus 1.17, that would be 1.47%. So that's already exceeding not exceeding to the right the critical level. So the value at risk at 99% would be somewhere between these two losses, between minus 23.45 and minus 8.99. Okay. So now I can either be simple, conservative, and just say that the credit value at risk is the worst of those two numbers, the biggest loss. So say that the credit value at risk is the 23.45 loss that you see here. So this would be, again, a conservative estimate. Or I can be a bit more fancy and interpolate between the two numbers, the 23 and the 8.99, which is this number here. Interpolate between these two numbers and find a 99% value at risk in between those two numbers, 14.8. So in either case, this is an estimate of the credit value at risk. Since this is just one firm, this estimate becomes quite different. But again, the point here is just to illustrate the main concepts. What we will do next is to estimate this value at risk for a portfolio, and then the distribution will be much more continuous, and we will be able to get a value without this big jump here. Okay, I'll do that in a second video.